In our approach here with oscillating perturbations, we chose the system initially to be in a specific energy eigenstate, the mth state, which we called psi-m. Now the application of the perturbation has changed the state of the system. So now there's a probability that the system's in some other state. We would like to know if we now make a measurement, for example, of the energy after the perturbation is over, what's the probability that the system will be found in some other state, say the jth state, which we might call psi-j. In the language we now use then, we want to know what's the transition probability from state m to state j.
In this model then, the probability pj of finding the system in state psi-j is, of course, just the modulus squared of the expansion coefficient. And that's the first order expansion coefficient we've calculated here. Remember, the 0th order one was 0 because we started out in state m, which we presume is different from state j. So we can therefore work out this probability that after the perturbation we're going to find the system in state psi-j. And so that would be this expression here. So we just squared up the modulus of that expansion coefficient we just worked out. So there are various terms in here. There's a sinc squared term here, there's a sinc squared term here, and there's this term here that's the product of two different sinc functions. Well, as we know, the sinc function, the sin x over x-like function, falls off rapidly once the argument gets much larger than 1. And here, for sufficiently long t0, that is, for a perturbation that's been on for a long enough time, either one of these two will be very small. Even if one of them was large, the other one would have to be small. So what will happen then is that as time t0 is increased, as we leave the perturbation on for some longer time, these two sinc functions get sharper and sharper, and eventually they will not overlap significantly round about our frequency omega here. And that means, therefore, we are going to lose those terms, that product, and we'll only be left with these two terms. That product of the two different sinc functions will go to 0 because one or other, or both of them, has gone to 0. So we're left now with this expression with two sinc squared terms in it. So we now have some finite probability that the system has changed from its initial state, psi-m, to a final state that's different, psi-j. This probability depends on the strength of the perturbation squared, we see that out there, and the modulus squared of the perturbation matrix element. So this is the actual matrix element that we're going to square up, the modulus squared of it, to get the result here. And that's the matrix element between the initial state and the final state with the perturbing Hamiltonian. Here just the time-independent part of it in the middle. With an oscillating field acting on an electron, then, the probability is proportional to the square of the field amplitude, because that's buried inside this hp0. And we're taking the square of that. And that means that the probability of this transition is proportional to what we would call the intensity, the power per unit area, because in electromagnetism, the intensity is proportional to the square of the electric field. So the probability of making this transition from state m to state j is proportional to the intensity of our light field, or electromagnetic field. In this expression here, what is the meaning then of these two different terms? Well, the first term here is significant if omega jm is approximately equal to omega. That is, if the energy h bar omega is approximately equal to Ej minus Em. Since we chose omega to be a positive quantity, this term is significant then if we are absorbing energy. That is, if J is a state that's above M. That means that we're talking about raising a system from a lower energy state to a higher energy state with this positive energy here. We note that the amount of energy we are absorbing is this amount h bar omega. The first term behaves, therefore, as we would require for the absorption of a photon. The second term is significant if minus omega jm is approximately equal to omega, so that, again, this becomes approximately 0. That is, if h bar omega is approximately equal to em minus ej. So if this is to be the case, since h bar omega is positive, that would mean that ej must be an appropriate lower energy than em. Again, since we chose omega to be positive then, this term is significant if we are emitting energy, falling from a higher energy state, psi m, to a lower energy one, psi j. We note that the amount of energy here that we are emitting is h bar omega. So this second term corresponds to the stimulated emission of a photon. That's the process used in lasers. Now, this is not the process that occurs in normal emission by, say, light bulbs or even the sun. The spontaneous emission of normal light, to understand that, actually requires that we quantize the electromagnetic field. And we're not doing that here. We're treating the electromagnetic field as a kind of classical field. And strangely enough, we actually get the so-called stimulated emission phenomenon out of this quantum mechanics, which mostly occurs really only in laser light. And we're not getting the much what we might regard as simpler phenomenon of the ordinary spontaneous emission, as it's called, of light. To understand that, as I said, we have to proceed much further with quantum mechanics, and we have to quantize the electromagnetic field. And that's something we'll have to leave for some other time.